Let us look at the concept of commutators in groups. Given a group G under the group operation star and A and B in G, commutator of A and B is A times B times A inverse times B inverse. Let's understand this. Let's say we have A times B times A inverse times B inverse equal to C. C is another element in the group. Now that implies A times B is equal to C times B times A. How did we arrive at that? We right multiply both sides by B. So B inverse times B gives us E. On this side, we get C times B. Now we right multiply both sides by A. So we end up with A inverse times A. So that is E. On this side, we end up with C times B times A. And here we are left with A times B. What is happening here? If we do this multiplication and we end up with E, that is the identity, then what happens? AB is equal to BA, it becomes. That means they are commutative. What happens if it is not equal to E? That means they are not commutative. They do not commute each other. So that is where this C comes in. It tells us how far from commuting they are. A times B and B times A. So C is called the commutator. By including it, we make A, B commute. So that A times B is equal to B times A. Or rather, A times B is equal to C times B times A. C is written as commutator of A and B. If A and B commute, then we do not require a commutator, which means C is equal to E. Otherwise, A times B times A inverse times B inverse equal to C, where C is in G but not equal to the identity. So we write this as A times B is equal to the commutator of A and B times B times A. So let me restate this. What this commutator does is it allows us to equate A times B and B times A. The set of commutators always generates a subgroup called the commutator subgroup. So commutator is written as the group identifier prime. So G prime is equal to the subgroup generated by the commutator of A and B, where A and B are in G. Every element of G prime is a finite product of commutators. So A1 times A2 times A3 dot 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 up to AN, where each AI is equal to the commutator of Xi, Yi for some Xi B Yi in G. Now we will look at examples and try to understand what is happening here. Now let's look at the properties. G prime is always a normal subgroup of G. The inverse of the commutator of A and B is equal to the commutator of B and A. The quotient group G by G prime is abelian. G prime is the unique smallest normal subgroup with abelian quotient. Just think about it. It will start making sense. Because remember, G prime contains all the elements of commutators. The quotient group G by G prime is the universal abelian quotient of G. That is the maximal. Now, how do we figure out this? Just for understanding purpose, look at this. G by G prime. G prime is the smallest. So that means G by G prime is the maximal abelian quotient of G. H is a subgroup of G. So the quotient group G by H is abelian. It's only when the commutator group G prime is in the quotient group. G by H. The commutator of X comma Y is equal to E if and only if X times Y equal to Y times X. That we have already seen. Set of commutators is not equal to the subgroup in general. In some specific groups, that might be the case, that the set of commutators themselves form a subgroup. But in general, they do not. So let's look at an example and see how all this works out. Let's take G is equal to S3. And we know S3 contains these elements. E, permutation 1, 2, permutation 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. Let me bring in the table of commutators. So here the group operation is the commutator or generating the commutators. So if the two elements A and B are one of these and one of these, then the appropriate commutators are these. Now E is always a commutator. So set of commutators is equal to what? Remember, this table contains all the commutators. So if you notice, apart from E, permutation 1, 2, 3, permutation 1, 3, 2, nothing else is there. So the set of commutators is equal to E, comma, permutation 1, 2, 3, and permutation 1, 3, 2. If we generate the subgroup using 1, 2, 3 permutation, we get E, comma, 1, 2, 3, comma, 1, 3, 2. And same is the case with respect to the subgroup generated by 1, 3, 2. That also generates the same thing. The only thing is it is permuted. So which means the commutator subgroup of S3 is S3 prime is equal to E, comma, 132, comma, 123 under the group operation. And this is always a normal subgroup of S3. So here both the non-trivial commutators generate the commutator subgroup of S3. But in general, for a group G, the set of commutators may not form a subgroup, mainly because the set may not be closed under the group operation or absence of inverses. That is why the commutator subgroup is defined as a subgroup generated by all commutators. So let's say we have C1, C2, C3 are the commutators of group G. Then G prime is equal to the subgroup generated by C1, C2, C3. So let's see how we can build it. So sometimes it is enough to use a few commutators to generate the subgroup. In case of S3, we saw we can use either permutation 1, 2, 3 or 1, 3, 2 to generate the subgroup. But since we are talking in general, that may not be the case. C1, C2, C3 themselves do not form a subgroup along with E. So in such a case, let's see how we can form a subgroup. So we initialize the Cayley table. So something like this. So we have the group operation E, C1, C2, C3. E, C1, C2, C3. Then we start filling up the table. So we fill the table with the products. So as far as E's are concerned, it's pretty straightforward. Just copy the headers. Now, C1 times C1, whatever is the result, you write it here. Similarly, start filling up all the cells. Now, it might happen that when you multiply two elements, say C2 times C3, that may not be there in the column headings or the row headings. So what do? We add a row and a column for it. So which means again we have to find the products for those rows and columns as well. Now once we have done that, we take the inverses for each of the elements. Again, some inverses may already be there, Some inverses may be missing. So for missing inverses, again add a row and column header for each of the missing inverses. So as you keep doing this, you will reach a stage where this table will be complete and it would form a subgroup. So here, what are we doing? By filling the table with the products and adding rows and columns for each of the products that are not there already, we are ensuring the multiplicative closure, or rather the closure based on the group operation, and taking the inverses for each of the elements. And if it is not there, adding rows and columns, we are making sure that it is closed under inverses as well. Associativity, we need not bother because that is inherited from G itself. Identity anyhow is already there. So commutator is something which helps us in equating A times B with B times A by incorporating it in the equation. That was commutators. Again, let me remind you, there is a link to a PDF file which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.